Hello, my name is Andrea Gorgerino. I'm the Director of Worldwide Field Application Engineers at EPC. The topic of our discussion today is understanding the impact of dead time in motor drive application. So let's start with the motivation. So we want to take a detailed look at the effect of dead time on inverter losses, and in particular switching losses, which are dominant in inverter applications. However, they're often not very well understood, and in particular, the dead time losses, which play an important role on the overall switching losses. But we will also take a look at the motor behavior and how dead time affects the system level behavior of motor drives. So first, a few assumptions. We are looking at a harsh switching three-phase inverter. And for the switching losses in particular, we will look at the single half-bridge cell. We also assume there is sufficient dead time for the self-body diode commutation, which is true in most load conditions, except at very light loads, light currents. We also assume the strain inductance is negligible, and the RDS on it is negligible to simplify the waveforms. So let's look at typical FET parasitics. The dominant parasitics are capacitances. So these capacitors are typically identified as CISS, CRSS, and COSS. And they can be written in terms of the gate to source capacitance, the gate to drain capacitance, and the drain to source capacitance. We also need to consider the body diode, which has a forward voltage drop VS2. For silicon MOSFETs, which have a body diode with minority carrier, we also have the reverse recovery charge QRR. So let's look at the operation of the half-bridge cell. S1 is on the high side and S2 is on the low side. S1 is on with a certain duty cycle and is feeding the motor inductance L with a constant current. These are what we normally consider to be called the transition losses or the switching losses. However, we will also be talking about dead time losses. And these are what we call the losses that happen during the body diode conduction time. Let's take a look at the switching loss of the high side FET S1. Shown here are the typical waveforms. The blue S1 command, and this is the control signal, which results in a certain gate to source voltage shown in red. So the input charge effects are that the CISS has a direct effect on transition speed. The faster this transition, the lower the switching losses. If we compare GaN FETs versus silicon MOSFETs, GaN FETs have very low input CISS, which means faster switching, which means lower transition losses. This is pretty clear. Now let's take a look at the low side FET S2 switching losses. Again, typical waveforms are shown here for the low side FET. The switch node in this case is driven by the inductor all the way into the full body diode conduction. This is known as soft switching. So in this case, CISS has no effect on the switching in any way. And the soft switching also means there are no hard transition losses. Of course, we need to allow enough dead time between an S1 and S2 to prevent shoot through. During this dead time, there are actually losses. And these are basically the forward voltage of the diode times the current and times the conduction time. If we compare the GaN FETs versus silicon MOSFETs in this condition here, GaN FETs have a higher diode drop, which would mean that there are higher dead time losses. However, we will take a closer look at this assumption and we'll show that that is not always the case. To understand why GaN FET will not necessarily have higher dead time losses than a MOSFET, we need to take a closer look at the output parasitics, which is COSS basically. So the COSS is affecting when S1 turns on. And you can see here when it turns on, S1 is basically discharging COSS1, and all that energy is lost in heat. So we normally calculate that energy as a half of COSS1 times V bus square. This is a common equation used. Now the problem with this equation is that COSS is not fixed. And so which value do we use for COSS1? Then we also said that COSS, the S2 does not have any switching losses, right? However, if you put a large capacitor in parallel with COSS2, it will impact the behavior of this converter. So how do we account for that? So we need to take a look at the nonlinear effect of this capacitance. So capacitor stores charge Q and E, and energy E. So first of all, the stored charge Q is the integral of the capacitance over the voltage, while the stored energy is the integral of the voltage times the capacitance over voltage. So these equations are not the same, and now we can use them to calculate accurate values. So we defined energy-related and time-related capacitances. First, the time-related capacitance, COSSTR, is the capacitance that I would need to get a particular QSS, while the energy-related COSS is the capacitance I would need to get a particular EOSS. So obviously, the nonlinear has an effect. So let's take again a look at what happens when S1 turns on. So the top set of waveforms are for the high side switch S1, and the bottom set of waveforms is for the low side switch S2. So when S1 turns on, we discharge the energy in the top switch capacitance, and we'll call that energy EOSS1. But happening at the same time, the switch node voltage is rising, and that is charging COSS2. So this charge comes from the bus, which is V bus, times QSS. And at the end of the turn-on interval, we have the energy stored in COSS, which is EOSS2. Now, we can compute the total energy lost during the turn-off of S1 due to capacitive effects. And that is the EOSS1 from the S1 turn-on. It is plus the energy provided from the bus to charge COSS2, and that's V bus times QSS2, minus the actual energy that is stored in the COSS2, which is EOSS2. And this is the full equation. So what happens instead when S1 turns off? So the inductor will pull current from the charged COSS2, and at the same time, it will pull current from the discharged COSS1. Since all of the energy is pulled by the inductor, there is no net turn-off energy lost because of the capacitance during this transition. So in summary, we can see that the capacitive ion is the EOSS1 plus the V bus times QSS2 minus EOSS2. Now, in motor drive application, typically S1 and S2 are identical. So this formula simplifies as simply V bus times QOSS. And since it should be noted that for GaN FETs, typically the COSS is much lower than a silicon MOSFET, this allows us to switch more efficiently. But we must also look now at reverse recovery effect, which is present when you have a body diode that's a PN junction. So we start with the low side switch S2 in the on state with the inductor current flowing through the device. So then we turn off S2. So this forces the inductor current to commutate to the body diode of S2 during the dead time. Next, at the end of the dead time, we turn on S1. S1 is starting to supply current to the inductor, and as S1 current rises, the current in S2 falls. Finally, S1 is carrying the entire inductor current. However, at the same time, the current actually reverses and starts to flow through the body diode S2 in the opposite direction it was flowing a moment before. This is what we call reverse recovery. And the energy lost during the reverse recovery can be expressed as V bus times QRR. And you can see that this is a very similar equation to the one for the COSS losses. So now we can combine the two and update the overall equation by adding the QRR losses. In this case also, when S1 and S2 are identical, which is common for inverter, motor drive inverter applications, this overall equation simplifies as V bus times the sum of QSS plus QRR. And for GaN FETs, this further simplifies since QRR is actually 0. So let's compare GaN FET versus silicon MOSFETs. Again, for GaN FETs, QRR is equal 0. But for silicon MOSFET, QRR reverse recovery only happens within the PN junction body diode. It is important to consider the QRR is not actually a fixed value. It is not very well characterized in the datasheet. And there is a number, but in reality, this number will worsen with higher temperatures. It will worsen with higher currents, also faster switching, as well as higher voltage rating, and also actually depend on dead times. In particular, longer dead times will make it higher. So let's take a look at all of these effects in an experimental setup. We've done some GaN versus MOSFET experiments using 80-volt parts. We designed a special 50 millimeter by 50 millimeter half bridge board for each of the FETs tested. They have identical layout as close as possible because, of course, the footprints are different. Each board was operating at 25% duty cycle, 300 kilohertz, with a 4.7 microhenry output inductor and output capacitors. Since we could not use a true 0 nanosecond dead time condition without shoot-through issue, we started with a 5 nanosecond baseline. And we made this loss to be our 0 by subtracting into all the further measurements. So then we started by adding 5 nanosecond to the total dead time and measured total losses. This is repeated until all the dead times have been measured for all the FETs. And then the dead time losses are simply calculated by taking the P loss minus the baseline. And finally, we did several experiments with varying dead time. We only varied either the rising edge or the falling edge, keeping the other one fixed. So these are the results for the impact on turn on. So this shows the turn on dead time results with a fixed turn off dead time of 20 nanoseconds. We used 3 different 80-volt FETs, 2 MOSFETs, black and red, and 1 GaN FET shown in blue. The results here were plotted at 10 amps, 20 amps, and 30 amps. Looking at the small dotted lines, which is the 10 amp load lines, the silicon MOSFET losses are quite low, or on the order of 1 watt. Not too far away from the GaN FET results. However, when you start increasing to 20 amps, the dashed line, and 30 amps, the solid line, we see a sharp increase in losses that gets worse and worse as you increase the dead time. Eventually, the MOSFET losses start to level off, but the MOSFET losses are now 2 to 3 times higher than the losses of the GaN FET. We're approaching about 6 watts on the last measured point. Now, let's look at S1 turn-off dead time with a turn-on dead time fixed at 20 nanoseconds. So the same current, same scales on both the X and the Y axis as the previous graphs. Now, in this case, we don't have any reverse recovery losses. The inductor is driving the switch node. The silicon MOSFETs perform much better, and that's because they have a lower voltage drop on their body diode than the GaN FET. The GaN FET losses are actually pretty much identical to the turn-on dead time losses because the losses in both cases are simply due to the voltage drop. But if we were to sum up the previous chart to this one, it is obvious that the GaN FETs wins with lower overall dead time losses. And therefore, we have proven the initial point that we wanted to discuss today. Next, we will take a look at our second experimental setup. This is a system level setup, which mechanically attaches a motor to a dynamometer. This is a hysteresis brake load, and it provides mechanical loading to the motor. The inverter is with the controller is actually electrically connected to the motor and is powered from a programmable DC power supply. This system allows us to take a measurement under various load and supply conditions and determines the performance of the entire motor drive system. First, we tested the motor drive of the previous setup with a 36-volt DC supply, 5 amps RMS in each phase of the motor, with a sensorless field-oriented control algorithm. On the left-hand side, we see the waveform for a 20 kilohertz PWM frequency and 500 nanosecond dead time. These are the typical conditions for a MOSFET-based inverter. Using higher switching frequency for MOSFET results in higher losses, and the dead time can also not be reduced further due to the MOS switching behavior. So next, on the right-hand side, we adjusted the dead time to 21 nanosecond, which is something that can only be achieved with GaN devices. In the waveform on the right, we are still switching at 20 kilos and delivering 5 amps RMS into each phase of the motor. So it's obviously already just by looking at the picture how much smoother the waveform on the right is. In particular, on the left-hand side, with the 5 nanosecond dead time, you can see there are 6 discontinuities in the current circled in orange. These discontinuities are responsible for the 6th harmonic of the electrical frequency in the torque, which create torque ripple. Based on the same measurements as the previous slide, we measured the spectral content using an FFT for the torque measurement of the motor. This is a direct measurement of the torque spectrum, basically. On the left-hand side, we have with a 5 nanosecond dead time, a 6th harmonic on the torque signal can be clearly observed. On the right-hand waveform, which is for the 21 nanosecond dead time, this 6th harmonic is clearly absent. This means that the phase current on the right gets converted into higher torque for the motor by removing the inefficient effect of the torque harmonics, which do not create any effective work. And this reduces mechanical losses. Now we will talk about the effect of reduced dead time on the motor phase current low frequency harmonics. Again, on the left-hand side, we have the case with 500 nanosecond, and on the right-hand side with 21 nanoseconds. Notice the clear difference in the time domain for the two waveforms. An FFT of the low frequency clearly shows the low frequency harmonics in the 21 nanosecond dead time can be significantly reduced. And this ultimately translates into reduced costs for filtering and operation. In summary, we can put all of the previous effects together and show the effect of reduced dead time at the system level loss. This table compares the operation on the left-hand side of the same inverter with 20 kilohertz and 500 nanosecond dead time, and on the right-hand side, the inverter operating at 100 kilohertz with 14 nanosecond dead time. So with a shorter dead time, the torque per amp is actually increased. And this makes the motor basically more efficient. So notice that the 100 kilohertz inverter actually has higher losses because it is switching faster. However, the overall system efficiency is significantly increased, again, because of the increased torques per amp. So this is the overall system level effect of reduced dead time. So let's take also a look at the audible emissions. We used here a simple iPhone app called Spectrum View. We measured the audio emissions from an unloaded motor operating from 40-volt DC supply, about 66 hertz. The green spectrum represents the background ambient noise floor. The red shows the audio spectral content for the case when the inverter is operating at 20 kilohertz using 1,000 nanoseconds, 1 microseconds of dead time. While in contrast, when we operate the motor drive at 100 kilohertz using 21 nanosecond dead time, there is significant reduction in the spectral content with an average reduction of 12 dB. can find more information here in these links. So this concludes our presentation today. Thank you for hanging in to the end, and I hope to talk to you guys soon. Thank you. Bye-bye.